Thank you very much. So I thought that, at the beginning of the day, just tell you about Circuit Insights and why we're having this event, which is, again, called Circuit Insights. So before that, let me just tell you that, yes, this is working. Just a little bit about myself. I just want to tell you about the last item, in fact, on this, but I do work at the University of Toronto, and I work in the area of analog and mixed signal design in general. But one of my interests or fun activities that I have is, in fact, Circuit Insights and also Circuit Intuitions. So Circuit Intuitions is a series of articles that I write for the Solid-State Circuit magazine, and Circuit Insights, which we started 3 years ago at ISCCC, is now part of ISCCC on an annual basis, also part of ESSERC, and also part of ASCCC as of this November. So why are we doing Circuit Insights, or why are we doing this? And the idea is that, we are at a time where things are getting more complicated. Bill Bauhill mentioned about the fact that when you started, it was 6 micrometer technology, and now we're talking about 2 nanometers. I guess Intel was talking about 18 angstrom, and so on. And so things are getting really, really complicated, far beyond what we've seen before. And so designing with these tiny devices that you cannot touch, you cannot see, it's becoming more difficult as we move forward. In fact, what we're doing is we're really using electrons to control electrons. And so there's a lot of abstract concepts. And when you look at some of the textbooks or papers, you'll sometimes see a lot of big formulas, and it's something that it's mind-boggling. And so the idea is that most students tend to think, okay, you give me a large circuit, I go and simulate. And so there's a tendency to just jump into the simulations and then see what the computers will tell you about this. And I think that's not the idea. In fact, I don't think you can go ahead and innovate anything in circuits if you just want to rely on formula. So what we're trying to do is to provide you with a bit of intuition and insights in this circuit so that you can actually see that it's easy and you can enjoy it. So that's the purpose of Circuit Insights and what we're doing here. And I'd like to emphasize that these intuitions and insights are really critical to innovations that we would like to see in future. In fact, one of the people who gave a talk at Circuit Insights, the very first one that we had in ISCCC 2021, was Willie Sanson. Willie Sanson, as you know, was an educator, researcher, and mentor at KU Leuven, and we all owe him a lot of gratitude for what he's done for the area of circuit design. But we had the pleasure of having him at ISCCC 2021 during a session that we called Joy of Circuit Design. And the idea was that we wanted to go to these people who have done work for many years and ask them to share part of that joy with the students. In fact, that video is available to you on SSCS YouTube channel, and I will invite you to look at it. But as part of that, we asked Willie Sanson and a few other people, what is their advice to new and aspiring circuit designers who are just starting their careers, most of you in this room. And he had 3 important sentences that I captured here just to remember him. He said, you have to leave the level of circuit design and go higher than that. He said, you have to understand what circuit design means at the system level. And believe it or not, most of the talks that we have today is essentially following his advice. We're going to tell you a little bit higher than circuit level so that you have that vision. He also mentioned this last sentence. He said, you have to know something about noise and something about distortion. And just to honor his vision, I thought I will include a little bit of, or tell you something about noise and something about distortion, although I only allocated 20 minutes to this talk, so I don't know I can tell you much, but I can tell you something about it. So before we move forward, I want to just give you the big picture, because you're going to see a bunch of talks, all very great in their own area, but I want to tell you that they're all very well connected, and their connectivity is through electronics, is through electrons. What do we call electronics is really the art of controlling electrons. This is, in fact, what you will be doing, hopefully, in the next 20, 30 years of your career. You're going to understand electrons. You're going to use electrons and you're going to control electrons. That's what we were doing. And when I say controlling electrons, it's really for one of three main purposes that I can highlight here. One is that we use electrons, or we control electrons for the purpose of storing information. So if you, if you look at this picture here, this is a very simple circuit that includes only one transistor and one capacitor. The role of this transistor is to control the flow of electrons that you can then trap on top of this capacitor. So if you put enough electrons here, you would consider it a 1. If you don't, you consider it a 0. So really what we're doing is that we're trying to control the flow of electrons to store on a capacitor, and they call it 0 or 1. If you look at the one in the middle, this is the one that we're controlling electrons to process information. Let's assume you have a signal and you would like to low-pass filter it, or you like to integrate that signal. So how do you do this? We are using electrons to do that integration, and we do this through a simple resistor and capacitor. We represent a signal as a voltage, that is essentially the electrons that create a voltage, and then we use a resistor to control the flow of electrons, and then we use a capacitor to integrate the electrons. And through this process, we are doing this operation that you can see through Laplace transform, and you can see it in your textbooks. So what are we really doing here is that we're using electrons in order to process the information, or in this case, the signal that we have. The last one here is communicating information. We need to talk on our cell phones, and that is what we do here. We are going to use a power amplifier. We use electrons to take your voice or whatever information we have, and then we amplify it, again, through the number of electrons, and we use those electrons and we feed them to an antenna in order to create an electromagnetic wave. And the electromagnetic wave doesn't need electrons. It can travel without electrons. But at the other end, at the receiver, those same electromagnetic waves are going to bring electrons together and recreate the signal that we have sent, or we've intended to send, from the transmitter to the receiver. So you can see in all these applications, and I mentioned to you that, in fact, if you look at all the electronic devices that you're doing and everything we do with electronic circuit, generally speaking, they actually follow one of these three. Either we're storing information, we are processing information, or we're communicating information. And in this process, in fact, the elements that we are using are mainly transistors. We're using transistors, resistors, capacitors, and inductors, and we do all of those things that I mentioned in terms of controlling electrons. But these elements that we use at the same time, they add noise. They add unwanted signal that may degrade the quality of our desired signal. And also there's a concept of distortion when the signal becomes too large. So again, as I mentioned, I will talk about that briefly. So this is the level higher than circuits, as Willie Sanson said. If you look at this diagram, this really summarizes all the talks that we have today. At the center of this, there is circuit design. And circuit design, of course, has its own non-idealities. It has noise, it has distortion, and so we need to deal with that. So we design circuits. We take pleasure in designing circuits. But we don't design circuits just for the purpose of designing circuits. We design circuits for one of the applications or the aims that we have for this. I should say in the same category, I've included data converters, because data converters are an essential component in electronics when you need to represent the information either in the form of analog or digital. And the transformation between these two is so essential to all the applications that we have that I decided to put that at the center of this universe. But if you look at this, circuit design can then be used for the purpose of image sensing. And that is the first talk after me on this circuit insights, and this is given by Albert. So he will talk about the use of image sensors in cameras, how they work, and how these components that I mentioned, which are essentially transistors, can be used to control electrons and, in this case, photons. We can use electronics for the purpose of navigation, to sense navigations, to sense pressure, and other quantities we're interested in. So I would categorize them as other sensors, and I'm very happy to have Tim with us, who will talk about other sensors. We can use electronics for the purpose of ranging, deciding what are the distance between objects, especially important for example, autonomous cars or other applications where you need to find distance. And we use electrons. We control the electrons to tell us what is the distance. And this is, the talk will be given by Arnaud on circuits for ultra-wideband. We then all know about machine learning. This is going to revolutionize, or maybe already doing this, our world of electronics and the world that we live in. And so this is, when we talk about machine learning, we should realize that there's a machine component of it. Of course, there's learning. And the machine part is all hardware, it's all circuits. And we are very happy to have Charlotte with us today to talk about circuit design for AI. We look at communications, another broad application when you're talking about wireless, when you talk about cell phones and other applications where we need to communicate without wire. And that is, the 5G, 6G standards. And again, we're very happy to have Ellie with us today to talk about this application. We'll look at the cars, the autonomous cars today. Again, another major application for electronics. And we're happy to have Fabio with us today. There are other applications, but they cannot be included all in one day. So for example, today we may not have any speaker who talk about human health, but obviously that's part of this, and hopefully we will cover it in other areas. I should also mention that at the bottom of this, I have electronic devices. We should not forget that transistors are playing such an important role, and there's so many different varieties of transistors, and again, we're not covering that today in this talk. So let me look at the time, and I have about 6 minutes because I want to stay on time. So I have 6 minutes to tell you a little bit about noise and a little bit about distortion, something about noise and something about distortion. So I'm going to start with the thermal noise of a resistor. This is the amazing part that I felt when I was a undergrad student, that the prof at the time told me that if you take a resistor and you go to the lab and you try to measure the voltage across it, what do you measure? And I said 0, unless you have a current source or a voltage source connected to it. You measure 0. And he says, well, let's go and try it. And we went to the lab, and we decided to do some simple measurements. And it was interesting that you observed some signals, and we didn't know what it was, but it was called noise, apparently. And it was due to the random movement of electrons that happens just because you're not at absolute 0 temperature. At any temperature, electrons move, and we know that movement of electrons means current. And that current is something that will turn into a voltage, and you will observe the values here. So I'm showing you 3 sample voltage waveforms that you may observe across a resistor. And in this case, I've chosen a resistor that is 1 kilo ohm at a temperature of 17 degrees Celsius and a bandwidth of 10 kilohertz. This is the bandwidth of the oscilloscope that you can set. And so you observe this type of behavior, but there's something very interesting about this noise. Even though it's totally random, there is some characteristic of that randomness that we like to know something about noise and use them later. One is that, for example, the expected value of these noise at any given time is 0. One is that the expected of that noise is squared is always proportional to temperature, resistance, and the bandwidth of interest that you're observing it. In fact, for a 1 kilo ohm resistor, you will observe an RMS value of about 0.4 microvolt. And of course, if you use a larger resistor, if you increase the temperature and you increase the bandwidth, that number could go much higher and could start interfering with your signal. One thing that is interesting is that formula is that you have 4 kTr, where K is a Boltzmann constant, but you have this being proportional to T and R and delta F, which means that if you double the bandwidth, you double the power of noise. It turns out that that 4 kTr is constant, irrespective of frequency, and that refers to the fact that we call it white noise, where there's a power spectral density across frequency, and they all will be identical, and that's about minus 168 dB per hertz for this case. The problem is that once noise is added to the signal, as I'm showing you here, if I tell you this is my signal, you don't know which part of this is noise, which part of signal, because they are now added together. And it's very difficult to distinguish the signal from noise, unless, as Willie Sanson said, we know something about noise and something about signal. Because if you know, for example, that your signal is in the range of 4 to 6 kilohertz. If you look at somebody's voice and you know that his voice quality and what we're hearing it is in a certain range. Let's say in this case, I know that the signal is between 4 to 6 kilohertz. And I also know that the noise that I have maybe has a range of 20 kilohertz and is a thermal noise and is white, then we know something about noise, we know something about the signal, and that information enable us to separate them to some extent. And you can all think about this, the fact that what we could really do is to filter the noise at least. We will create a filter that has exactly the bandwidth of interest, which is 4 to 6 kilohertz. We'll let all the signal to go through, but we only let 10% of the noise power to go through. And that is amazing. Once we do this, we can actually recover the signal. So this is just pictorially showing you that if the input noise is white as shown at that orange at the top, and I have a filter, very simple filter in blue that has a bandwidth of 4 to 6 kilohertz, then the noise is going to be shaped by this shape of this filter. And once I do this, and I go back to signal plus noise, go through this filter, and you can see what I observe now. The recovered signal resembles a lot more to the original signal than what you have as signal plus noise. One thing that's interesting in terms of intuition is that, okay, we understand this in the frequency domain, you go through the filter, but what does that mean in time domain? It turns out that the concept of bandwidths that you look for a signal is closely related to the rate of change of the signal. So when I tell you that the signal of interest has a bandwidth between 4 to 6 kilohertz, in a sense, I'm trying to tell you what is the minimum and maximum rate of change for that signal. Now, noise may come at a much higher rate of change or much lower rate of change. What I could do is that I could somehow in time domain, look at my signal, and whenever the signal is going too fast, I say this must be noise that is doing this, because my signal is only going at maximum this rate. So by really limiting the rate of change of the signal in the time domain, I'm essentially doing the same concept, and that is what we just utilized. I mentioned that we need to talk about distortion, but unfortunately there's not much time. So I thought I'd just bring this picture from a very famous classic book from Willie Sanson, Analog Design Essentials. This was published in 2006, and I think every one of us in this field are really using that book, and we've really learned a lot from it. Just a nice picture showing that as you go and increase the value of the input voltage, and you look at the output voltage, at the beginning, when the input is very small, you just observe noise. But as you increase the level of voltage, you go above noise. Now you observe the signal being amplified. But as you increase it beyond that, then you see a nonlinearity and distortion. So here's a summary of what I said. Innovation in circuits is usually tied to our intuition and insights. And so this is why we have this event today. Intuition and insights help us to feel at home with the circuits, to make it easy and understandable. And hopefully they're no longer a mystery. You can really sense them and save significant time in design time, and also help us avoid catastrophic failures. Noise, I mentioned, is random, yet we can characterize it and we can mitigate its effect. Noise is not always bad. We didn't have time to talk about this, but we can actually use this. When noise is negligible and signal is large, we need to worry about distortion in that case. So we don't have noise, but we have to worry about distortion, and that's what I mentioned about the analog design essentials. I just want to have one slide to tell you that there's a lot of resources on SSCS. Aside from the magazine that has always at least 3 tutorials aimed at students, these are Circuit Intuitions, A Circuit for All Seasons, The Analog Mind by Behzad Razavi, and the Shop Talk, What You Don't Learn in School by Chris Mangelsdorf. We are very happy to have Chris with us today as one of the speakers. There's also a YouTube channel of Solid State Circuit Society. You can find tons of material on this for learning and for pleasure. Past circuit insights, in fact, are on SSCS YouTube channel. You have access to all the PDFs of today's event, and you can go and look them up. And as I said, I like to recommend Willie Sanson's Analog Design Essentials from 2006. Thank you very much.